Well, thanks for allowing me a chance to speak and share some experiences. I'm Lyndon Lamborn, and a lot of the work that went into this presentation was really a big help was Jim here. I thought I'd mention that really it's his work too. Some of my background, I have pretty strong ties right there to the Wasatch Front. I grew up in Logan, about 35 miles northeast, and graduated from Utah State. My first job out of college was at Douglas Aircraft. And as you might guess from these pictures, at least the one on the left, sitting out on the ramp, the flight test ramp, we were delivering MD-11s to Federal Express in this livery. Quite the beautiful aircraft. And and then I showed you to the right pipeline. In 1995, I had the opportunity to go to Alaska on vacation, and as we're driving through the countryside, saw a sign that said, "Hey, tour a pipeline pump station. Tours are given like 3 times a day." So I thought, boy, that sounds kind of interesting, and so this is pre 9/11, of course, when it was possible to tour a pump station of a pipeline. So I took that tour, and that kind of piqued an interest in me on pipelines. So after I spent 30 years working with McDonnell Douglas and Hughes helicopters and Boeing helicopters. I retired and took a job in pipelines. And by the way, I very much appreciated some of the narrative about the CF-18 by NRC Canada. I remember many a time in McDonnell Douglas team meetings, Sandy McDonnell, who was our chief executive officer at the time, spoke with great pride about the CF-18, the great product that the McDonnell Douglas was providing to the Canadian Air Force. And my first mentor at Douglas Aircraft, Art Shaw, he was the chief engineer for the T-38 landing gear. So some of the discussions that have taken place here in this workshop are near and dear to my heart. And oh, by the way, I saw on the list of participants the names Moser and Gillenskog. As a Boy Scout in Logan, Utah, I delivered eggs to the Mosers and the Gillenskog. So just in case there's a family tie there, just wanted to shout out, hey, it's a small world. And okay, so now I've got these two pictures up here. I want to ask you to think about this for a minute. Do you see any commonalities here? Just looking at these two pictures, what jumps into your mind in terms of commonalities? And I just wonder if I can get the chat window up here. Whoops. I can't really. Oh. Do I have any answers to this question? What kind of commonalities do you see? I can't get the chat window open, so anybody?
Tubes.
Tubes, okay, tubes. All right, things pushing down tubes. All right, you're pushing air through engines, you're pushing fluids through the pipeline. Okay, I like that. What else? Well, aren't they both transportation companies?
Yes.
Did that cross anybody's mind?
Yes.
Yes. This is all transportation, right? In ENBRIDGE Liquid Pipelines, we deliver 2.8 million barrels per day of product. FedEx, I don't know how much weight they've delivered per day, but they probably deliver quite a bit of tonnage per day. So very, very common. Any other thoughts out there? What about the consequence of an incident? How much does it cost if a FedEx airplane crashes and it's a complete loss? Maybe $100 million? Well, guess how much it costs if we have a rupture or a large leak in a pipeline? Okay, very similar in magnitude. We have essentially the same mantra, the same goal. We want to deliver our product as safely and as reliably as possible. And that's completely tied to our profit, is to be the safest, most reliable transportation company on the planet. So hopefully that kind of grounds our discussion as to what we're after here is very, very much the same. So as I moved, the other thing I wanted to point out is our maintenance of the aircraft and our maintenance of the pipeline is all geared toward achieving that reliability and that safety. And that is the first concern and almost the only concern. Okay. So you're saying, okay, how much pipeline could be out there? There's not that many pipelines. Well, ENBRIDGE is only one operator. And what you see on the screen here is 17,000 miles of liquid pipelines. We also have a large gas distribution network. I think their mileage is similar. But I'm currently up here in Edmonton. Get my laser pointer working here. So I'm up here in Edmonton, and I'm a Canadian resident in addition to being a U.S. citizen. So all of this pipeline system, the reliability management and integrity management is done here in Edmonton, believe it or not. And in the 17,000 miles of pipeline, delivering 2.8 million barrels per day, we are responsible in meeting all our regulations and reliability targets, and all the inspections that are done are all specified here in Edmonton. Actually, all the remote control of these pipelines is also done here in Edmonton, by the way. So that gives you a feeling for what we're involved with. Some other similarities, which many of you probably thought of, is the threat of cracking. So along the top here, I've just grabbed some pictures of cracks in aircraft. Looks like mostly aluminum. Of course, I was highly involved with this during my career in aerospace. And so I expected to see much the same when I came to the pipeline world. And sure enough, some examples of pipeline cracking is along the bottom. I carefully chose pictures that didn't have anything to do with ENBRIDGE, so that this is just public domain stuff. But as you can see, we have basically two types of cracking in pipelines. We have cracking associated with the seam weld. When the pipelines are formed, they have longitudinal seams that are welded together to form a pipe. And then we also have what we call stress corrosion cracking, which is sort of similar to what you talk about in aerospace, but is a lot more highly advanced corrosion, as you can tell here from these photos on the lower left. So managing this cracking is a big concern for us. And in that 17,000 miles of pipeline, we need to do inspections. Now, just like you do aircraft inspections over here on the upper left. And you have many, many types of different types of inspections. We do the same thing in pipelines. Now, pipeline inspections, you see on this upper right-hand corner, with liquids, we're able to run ultrasonic inspection tools. These are robots that run down the pipeline. Because we have liquids, we can use the liquid as a couplant, and we shoot our ultrasonic beams into the pipe steel, and we get returns. And this is illustrated down here on the lower left. There's a cool video, several cool videos out there by inline inspection vendors that show how the pipeline runs down, the inspection tool runs down the pipeline, and it bounces these sound waves through the pipe wall. And when you have a crack, there's a reflection that's collected by the sensor heads. I included a link up here in the title in case some of you want to watch that video. So this is how we do our inspections, and this is very, very similar to aircraft industry inspections. We usually don't send people down the pipeline like in the James Bond movie, putting people down the pipeline. Although in some larger pipelines with water, there have been divers go inside pipelines, but that would not be something I'd want to do. So in general, this is how we inspect our pipelines for cracks. And we can run a crack tool on a new pipeline. It might only see maybe 5, 10, 15 cracks. On an older pipeline, it might see 5, 10, or 15,000 crack features that we would need to just look at, assess, and decide if we need to go out and repair. So that's kind of the crux. Here's on the lower left, I point out the typical way to form a pipeline is to take a sheet or plate steel and then form it into a cylindrical cylindrical section, and then it's welded here, a seam weld. We used to always say in helicopters, there are really two types of welds in helicopters. There's the type that have failed and the type that will fail. And so I was very, very leery of welds in pipes, and rightfully so. You have the opportunity for defects in your seam weld. And because pipelines are operated with pressure fluctuations, I've shown here where my laser pointer is. This is a 3-month time history of pressure at a pump station. And these fluctuations are generally coincident with what we call batch processing. We'll have a batch of oil from Imperial. They'll want us to run for maybe 36 hours, and then we need to switch and go over to Chevron. They'll have a different type of commodity they'll want to ship for 24 hours, and then we'll go back to another. And thus we have to reduce the pressure while we change over the valves and introduce the new commodity, and then we ramp back up to operating pressure. So this is the kind of pressure fluctuation time history you would see. And of course, this internal pressure change results in a cyclic hoop stress change in the cylindrical pipe, which all of you understand immediately that gives you a cyclic stress with R greater than 0, particularly at this seam weld. And if you get a crack feature here detected by your crack tool that gives you dimensions, you can do crack growth analysis on that and predict how long it's going to last. So again, the similarities between aircraft crack management and pipeline crack management are huge. So here's what a typical fracture might look like. Again, this is public domain information. You might have down here on the ID of the pipe, a lack of fusion in the weld, which was the initial flaw in manufacture. And then this lighter colored tan, you probably can't see the fatigue striations there, but I can see them on my screen at least. And then, of course, you got the fast fracture, which is basically what the final fracture surface. So this would be a typical seam weld flaw that could grow and become a threat to the pipeline integrity that we're trying to avoid, and we invest a lot of money to avoid those incidents. In fact, you say, well, how much could these inspections really cost, Lyndon? You're just talking about pipelines here. Well, I have 155 segments. We usually inspect between 3 and 7 year intervals, maybe average of 5 years. So I'm doing about 30 inspections a year on pipeline segments throughout the system. And a pipeline inspection can cost up to $1 million. Usually a little bit less than that, depending on the length and the age of the pipeline. But that, after you do 30 inspections a year, and then you have to do excavations. You want to verify that your inspection tool is working properly. And of course, it might see some severe features that you feel might be an integrity threat that you go and excavate. An excavation can cost between $100 to $200, even up to $500,000. And so between the excavations and the inspections, pretty soon you're talking about some real investment, but every dollar spent is reducing that risk of crashing the MD-11. And so every dollar spent is paid back many times over in risk reduction. And so our investment in inspections and integrity excavations, inspections right on the pipe to correlate our information in the field to what we see with the tool, all that investment is highly justified and proven. So when I got to the pipeline industry, I was familiar with AFGROW and crack growth and looking at the threshold for no growth, which we use a lot in helicopters because helicopters are just flying fatigue machines. So we rely on characterizing the threshold for no growth quite a bit in helicopters. And imagine my surprise when I got to the pipeline industry, and the only thing anybody talked about was region B on the DA/DN curve. And in fact, Jim could probably speak up at this point and echo his surprise. All the testing that we can find, or at least large proportion of the testing we could find on pipeline steels, focused only on region B. There was nothing done outside region B. And so I was proposing, well, why don't we do some characterization of regions A and C and use the entire tri-region curve? Imagine my surprise when I got pretty much a negative response. I was facing this situation, one of my favorite cartoons. Instead of evolution theory, you might put in here fracture mechanics theory, modern fracture mechanics theory. And the response I'm getting from most of my peers in industry is, this is hogwash. We don't need this. Region B is good enough. Even though we're spending hundreds of millions of dollars in crack management, all we need is region B. And so I'm stuck here on the second panel right now in the pipeline industry. But I'm trying to move us toward this third panel where you see the emerging animal from the primordial soup here, that evolution in theory, that fracture mechanics, modern fracture mechanics can be useful in the pipeline industry. And so that's kind of the mountain I'm climbing right now. So I asked Jim to help me look into establishing delta KTH, the threshold for no growth, for some pipeline steels. And as we kept peeling back the layers of the onion, I found some more data, and Jim found some more data, and before you knew it, Jim felt he had enough data to actually build a tri-region curve for a range of pipeline steels. Now, you say, what is X60 and X70? These are pipeline grades. 60 refers to 60 KSI yield strength, and 70 refers to 70 KSI minimum yield strength. And so for the first time, just in the last couple of months, we've actually have pipeline steels in an AFMAT entry. And this is a landmark event. I'm very excited about it. And hopefully we'll get to do the others because that is only scratching the surface. The base metal, we do a lot of analysis for cracks in the weld, and so we'll need to characterize that, which the industry pretty much knows that it's a little bit different. And then we'll have to do also for these other alloys, both base metal and in weld. So just characterizing the material, which is almost an assumption for aerospace materials that your materials are highly characterized and you have robust database information to go on immediately. Such does not exist in the pipeline industry. So my last slide here. So we're really at a grassroots building block stage in the pipeline industry for use of advanced fracture mechanics. We're currently using it for these simple things, but these things have already had a huge impact. If we have to shut down a pipeline, it can cost us $50,000, $70,000, $80,000 per hour. And if we can avoid that through some advanced analysis techniques, obviously that's a good payback. We are projecting in the future to use this aerospace level type analysis, particularly for root cause analysis. We feel like we learn a lot from our incidents in the pipeline industry, similar to what you folks do in the aerospace industry. The root cause corrective action, a lot you can peel back a few more layers of the onion when you have advanced fracture mechanics to help you understand the stress states and the crack growth trajectories, as you know. And then when I say a level 2 analysis method, for those features that are difficult to get to, say I have a crack underneath the Missouri River that I wouldn't be able to get to fix. I have to schedule a new pipeline replacement. I'd have to drill underneath Missouri River. I'd have to get the Army Corps of Engineers involved. It's about a 5-year process. And so if I can do some more accurate analysis of that particular crack, that can be very, very valuable to us. And in addition to mainline, which I'm in charge of, we also get cracks in some of our storage facilities, which can benefit, have already benefited from AFGROW analysis. So thanks for your attention. I guess it's time for questions, if there are any. I know this industry is probably a little bit different than what you're used to. I'm still socializing the use of advanced fracture mechanics and in the industry. So if I can, maybe I can get the chat window up here somehow.
Well, Lyndon, I want to echo again that, it's good for us to get other perspectives into the AFGROW workshop. So I want to thank you for being willing to give the presentation.
Happy to do it, Tim.
Okay.
There's a question.
Yeah, there's a question up on the chat. You see it?
I can't see it. I don't know how to.
I read it to you.
Yes, please.
Okay. is the industry implementing any pipe manufacturing changes, for example, to welding to try to improve new installations?
Well, there's been a continuous, that's a great question. There's been a continuous evolution of improvements to welding. And it's applicable to both the long seam weld and the girth welds. And yeah, because inspection techniques and radiography and ultrasonic inspections have been improving over the years, over the decades. The specifications and regulations have tried to keep pace pretty much and enforce better and better quality going forward. So that's a great question. Yes.
All right. Well, good. Thank you, Lyndon. That was a really good presentation.